Okay, so let's transition from our discussion of sensation, where we're collecting information from the outside world, and let's start talking about perception. Remember, perception is how our brain is going to interpret the information coming from sensation. So, looking at this picture, there are a couple of different interpretations possible. It could be that what you're looking at is white paper with blue circles with a white cube floating in front of the blue circles. So if you look at the X, it really becomes obvious that there's a three-dimensional cube, what's called a Necker cube, emerging from those blue dots. And it's possible that what you're seeing is white paper with blue circles and there's a cube in front of the circles. Or maybe what you're looking at is white paper with holes, and you're actually seeing the blue background through the holes. And behind the paper is the white cube, and you're just catching glimpses of the corners and things through the holes in the paper. So let that interpretation sweep over you for a second. It's funny because based on your interpretation, you will either think you're seeing the lines continuing, the lines of the white cube continuing across the white paper, or you'll see it as those white lines being missing because they're behind the paper. The white background, whatever it is that we're looking at, the white cube and the background are the exact same color. But if you perceive the cube to be in front of the paper, you'll actually perceive the cube to be a slightly different shade of white, so that you almost feel like you can see the lines and where they are distinguished from the background, even though that doesn't really exist. It's all in your mind's eye. It's in the eye of the beholder. Okay, using that cube is a nice transition into the discussion of figure versus ground. Basically, how do we figure out, how do we determine what is the figure, the thing we should be focusing on, and what's the background, the stuff we can just ignore, the irrelevant stuff? Depending on your perception, you either see this as a white goblet with a blue background, or you see it as two blue faces with a white background. Now, the interesting thing about figure-ground perception is that you can see that there's a vase. You can see that there are two faces. But you can't really have a vase and two faces simultaneously. Your brain kind of hops back and forth between vase or faces, vase or faces. Something has to be the figure and something has to be the ground. And while it's true that your brain can really quickly hop between the two alternatives, something has to be the figure for the moment and something has to be the ground for the moment. This is that same picture from the first slide for this chapter that I showed you. And is it a man taking steps, or do you see the white arrows? You can't see both. If you're seeing a man, then the arrows just become the white part that fills in the spaces. If you're seeing the arrows, then the man becomes the black part that fills in the spaces. You have to hop back and forth between them. So part of how we determine what is a figure and what is irrelevant stuff that's just part of the noise behind the figure is we follow certain grouping rules. Now, I use the term Gestalt in the title of this slide. A Gestalt is it's a German word that is hard to translate into English, but it basically means a coherent whole. So how do we make coherent wholes out of the information that we're perceiving? I'm using all visual illusions or visual examples, by the way, because they're the easiest for me to display. Some of my, when I'm in class and stuff, the audio doesn't play correctly when I try and do auditory examples, things like that. But the assumption is these same laws or these rules apply to all of your sensations, whether they're sight, sound, smell, touch. I left something out. Taste. So a Gestalt is a whole that is more than the sum of its parts. So what does that mean? When I was an undergraduate, my instructors would oftentimes use that phrase, the whole is greater than the sum of its parts, like that meant something, and I never really understood what they were talking about. This is not my most flattering chapters lecture, is it? Because a number of things sort of escaped me during my my training, and this is one of them. It's, what do you mean? How can a whole be greater than the sum of its parts? But what they were talking about is that in the study of perception, in our attempt to understand how the brain makes sense of the information coming up from the senses, you can't necessarily break the object of your perception down into its smallest, most elemental parts, put it back together, and have it make the same amount of sense as if you were to just analyze the figure as a whole. Let me show you some examples of what I'm talking about. On the left, you've got an example of a grouping rule called proximity. One of the things that our brain assumes is that if items are closer together, they are part of the same whole. If they're farther apart, they are not part of the same whole. So your brain first guess will assume that picture is depicting 3 pairs of lines. Maybe it might go to the next level and think it's depicting striped wallpaper or a striped shirt or something where the pattern might be asymmetrical like that. But it doesn't think to itself, those are just 6 independent lines. It thinks that those are 3 pairs of lines. In the middle, we've got continuity, where your brain assumes that you've got one straight line and then a curved line overlaying the top of it. Your brain does not make the crazy conclusion that you might have the straight line is actually a series of dashes that happen to be the spaces between the dashes being covered up by the curved lines that are actually a series of arcs that are not really touching each other. And your brain doesn't think like that. It goes, that's a straight line with a curvy line on top of it. That's called continuity. Another example of continuity would be if you went to a baseball game and at the 7th inning stretch when they sing a song and the teams are in the dugout and you're not seeing them, when the teams come back out, you don't think, oh wow, a new game. Who's playing now? The assumption that you're still at the same stadium, that nothing's changed, you're going to conclude the same teams are still playing. That's continuity. That's your brain's assumption that things that are together and there hasn't been a break, that it's all part of one figure or one group. On the far right, we have the concept of closure. And on the left side, you can clearly see a white triangle. I mean, it's so obvious that there's a white triangle there, right? Whereas on the right side, it's not as obvious. It doesn't seem like there's as clear-cut a triangle on the right side. On the left side, the reason why you see a white triangle so clearly is because those arcs, I guess you would call them, that appear to be being obscured by a white triangle. The best explanation for that orientation is that they are being obscured by something. Because why else would you have arcs? Circles make more sense. 2 concentric rings with something obscuring part of it makes more sense than to say there are 2 arcs with a dot in the middle and they just don't have any kind of closure on them. So your brain fills in a triangle because that's the best explanation and it fits the evidence, right? It's just a super easy conclusion to draw. On the right side, while a triangle is visible, it's not as dramatic because you've got closure on the arcs. And so now you have like partial rings, and that makes more sense. It's a perfectly fine organization, so your brain doesn't have to come up with something else to explain what they're doing. So closure is our tendency to fill in the blanks to make the figure make sense, because sometimes things are missing. And so you go ahead and say, it must be obscured by something, or I'm just not seeing all the data. It's still one continuous form. All right. Oh yeah, I drew some things over top. I forgot I did that. Okay. Now let's get into depth perception. How do you know that some things are closer to you and some things are farther away from you, just visually? And is this an innate skill? Well, researchers have attempted to figure out at what point in our development we for sure can perceive distance by using this apparatus that you see on the screen, which is called the visual cliff. So you can see the baby's kneeling on this fabric or paper that has a pattern on it, and that on the floor, at least 3 feet below them, is the same fabric or paper. And they've got that plexiglass so that if the baby does choose to go ahead and crawl across to its mom, it won't fall. Sometimes the babies do make the wrong choice and they go ahead and crawl over. Most babies who can crawl will refuse to cross the visual cliff. They can tell the difference between the size of the objects on the paper that they're kneeling on versus the ones that are down on the floor, and they know that depicts height, and they know that they shouldn't crawl off of it. So very early crawlers, within 1 day of learning to crawl, babies will refuse to cross the visual cliff. So that kind of implies that they've got depth perception. At least they learn it very quickly as they become familiar with moving around the world. You can't rely on their depth perception to protect them from smaller cliffs. They've done this test with babies using like a 6 to 8 inch cliff, which is more like the height of a stair step, and they'll climb across that. So they can't really, the smaller distances they don't notice as well. You know, subtle differences in the sizes they don't notice as well. So you can't trust your baby not to crawl off the stairs or crawl off the couch or whatever. But a higher distance like this, they'll refuse, and that implies that they understand depth. Now, how do they perceive depth? Well, one way, or for sure all of us adults have binocular methods for perceiving depth. Our eyeballs are on the front of our face, pointed in the same direction as each other, just like other predators' eyeballs are. So you've got, you know, owls and bears and cats and stuff that have their eyes on the front of their head so that they can train both eyes on one object at the same time. That's what we call binocular vision. Predators have binocular vision. Prey animals have monocular vision. They have 2 eyes pointed in different directions, so it gives them a better view of the stuff around them, so that they're more likely to see a predator trying to sneak up. So here we have binocular vision. Okay, so in this picture we've got the 2 eyeballs, right? And they're looking at different objects. Okay, one cue that binocular vision gives us to depth is something called retinal disparity. A couple segments back we talked about the retina. That's the image that's falling on the back of your eyeball. And if you have slightly different views of the object, your brain assumes that the object must be closer to you. So if we look at this picture on the right, we've got the person looking at the finger that's closer to their face than the tree, right? And if you follow the line of light reflecting off the finger and where it's landing on the retina, you can see that that's landing in a different part of the eye. In fact, you can do a little test right now while you're listening to me talk. You can hold your finger out in front of your face, like maybe a foot away from your face, and then alternate closing your left eye and then your right eye. You've probably done this before spontaneously, most of us do. And you see your fingers seeming to hop back and forth, right? That's because each of your eyes is looking at your finger from a slightly different angle. So with one eye closed, it looks one way. With the other eye closed, it looks a different way. With both eyes open, you get depth. So when it's closer to your face, there's more retinal disparity. The images are more different. As the person looks farther away at the tree, the 2 images are virtually identical. And so even if they close one eye and then the other, the tree doesn't seem to move. They're seeing exactly the same thing. So the greater the retinal disparity, the closer the object is assumed to be to your face. Convergence is how much your eyeballs have to turn inward in order to look at the object. So items that are closer to your face, you're going to have to cross your eyes more to continue to look at the item that's closer to your face. And that's going to send a little muscle cue up to your brain that your brain calculates in conjunction with the retinal disparity to figure out how far away the object must be from your face. So if you're really having to turn your eyes inward and the 2 images that are landing on the retina are very different from each other, your brain will think, okay, that item's really close to my face. Whereas if your eyes are basically straight in the socket and the image is roughly the same, your brain will conclude, okay, it's farther away. So these binocular cues are really sort of a mathematical computation that your brain does of taking the image plus the position of your eyeballs into consideration to determine distance. Now this works great for, like, I don't know, 10 feet, something like that, maybe 20 feet at the outset. Once things get much farther than that, your eyes are going to be pretty much straight in the socket as you look at anything. So how do we know how far away something is when it's a two-dimensional image, or if it's far enough away that your binocular cues aren't working well enough? So how do we do that? Let's talk about it. Okay, we're going to use this nice picture from Le Conner Tulip Festival as our example of some monocular cues that help us to perceive depth. All right. First off, we have what when I was a student they called overlap, but I guess the world's gotten more complex, so we need a better name for it, so we'll call it interposition. So interposition refers to how the things that are closer to us will overlap or obscure our vision or our view of the stuff that's farther away. So if we look at the tulips, you see that the ones that are closer are blocking our view of the ones that are farther away, and so on. And the rows that are closer to us block our view of the rows that are farther away. Okay, that's interposition. Relative size. The tulips that are in the foreground look much bigger than the ones that are in the background, right? They're things that are closer to us appear bigger than things that are farther away. Linear perspective. These rows are perfect for this because you know that the farmer planted these tulips in straight rows, right? With the dirt in between is parallel to each other. But as we look at the picture, it seems like the rows are like coming together in the distance, right? They don't seem parallel the whole way. That's linear perspective. As two parallel lines move into the distance, they seem to come together in the distance, like that. Texture gradient. Things that are closer to us, we can see more texture and more detail. You can see clearly that these are, you know, red tulips with white edges on them in the front. If all we had was the distance view to look at, we would think these were just solid pink tulips, right? We have more texture available to us in the front, so we can see more detail. You can see it in the weeds between the rows in particular too. You can see the texture of the leaves in the weeds that you can't see in the distance. Relative height. The things that are closer to us in the field of vision will appear lower in our visual field, and things that are farther away from us will seem to go up in the distance. Now you might have been looking at this picture and thinking, well, yeah, but it's on a rise, it's on a hill. Even if you have a perfectly flat subject, it'll seem to rise in the distance. It's part of how our brain processes that information. I've noticed even in reasonably small areas, like when I'm lecturing in my classroom that only seats, you know, maybe 50 people, it seems like the rows in the front of the classroom are literally lower in my visual field than the rows that are farther back. The ones in the back row seem up higher. That's relative height. So one way to look at it is not only do the parallel lines horizontally come together like the blue lines depict, but if you think of the ground and the sky as parallel lines, they seem to come together in the distance also. Relative brightness. You can definitely tell that it seems like there's more illumination in the foreground than there is in the distance, and that has to do with just distance. Alright, so here we have a perfect example. We have railroad tracks. You know those are parallel, right? So I've got two red bars. Which of the red bars is longer? It looks obviously like the one on the top is longer, right? I mean, it's, you know, you're in a psych class, you know there's a trick and stuff, but I mean, come on, the one on the top absolutely looks longer than the one on the bottom. I mean, there's no, I made the bars, and every time I see the slide, it's so obvious that the one on the top is longer, right? But when we move them together and we get rid of those you know, distance cues, suddenly we realize that the two lines are the same. What's working here is that we've got cues like linear perspective at work, right? Like you can see that these parallel lines are coming together in the distance. So we know that the tracks in the foreground appear farther apart than the ones that are underneath the second line. So we know that the second line has to be farther away from us. We see more detail, right? There's more texture visible in the foreground than in the area underneath the second line. There's more brightness in the foreground than there is under the second line. There's more, the foreground is lower in our visual field than the tracks are under the second line. I mean, pretty much everything I just talked about helps to point us to the interpretation that the second line has to be farther away than the first line, which is in the foreground. Then you take into account that the red line in the foreground is only spanning the middle two tracks, right? And the line in the distance is spanning all four tracks. And we know it's farther away, and it's able to span all four tracks. We come to the conclusion that it's got to be bigger because it's spanning all four tracks. Plus, your brain assumes that if the two images being cast by those red lines are the same size, if the image landing on your retina is literally the same size, but all the cues are telling us that the second one is farther away, your brain makes a little calculation and comes to the conclusion that the one that is farther away must be bigger, or else it would not appear the same size as the one that's nearer, right? Because remember, relative size tells us nearer things should look bigger than farther things. So all those factors come together and we make the wrong conclusion that it's got to be bigger. But I don't know if, again, remember I talked about that show called Your Bleeped Up Brain. Is that really a bleeped up functioning of your brain, for your brain to conclude that the one that's farther away what must be bigger? Every cue is telling us that it's bigger. It should be bigger. It just happens to be that when you're in a psychology class, sometimes we set stuff up, or if you're playing certain kinds of games or whatever, they want you to make the wrong conclusion. But in real life, that's a really useful skill, to know that the one that's farther away must be bigger, given all the cues. All right, well, that's enough on distance. Let's go ahead and take a break, and we'll come back and talk about other aspects like perceptual constancy.